Hello everyone. This video covers sections 4.4 to 4.6 on the book. The two main concepts they're going to study are spanning sets and linear independence. So let's start with the first definition, which says the following. If every vector in a vector space B can be written as a linear combination of k vectors, then we say that B is a span. A span just means generated or created by those vectors. And then we call B1 to BK a spanning set of B. So what that means is that these vectors, remember when we say vector space, it doesn't mean that these have to be vectors. This could be matrices or polynomials or whatever. So what that means is that for any vector or polynomial or matrix or any object that belongs to the vector space, if this is a spanning set, that means that any of these vectors is just a linear combination of this one. Okay, consider the following vector space. Let's say that B is equals to R3. Remember, this is the set of all the vectors in 3 dimensions. So in general, any vector in 3 dimensions look like this: A, B, C, where A, B, C are any real numbers, and this belongs to R3. So this is the general vector. So in general, that's how a vector in 3 dimensions looks. A, B, C are any real numbers. Okay, now let's say that we have the following 3 vectors. Let's say that the first vector is 1, 0, 0. The second vector is 0, 1, 0. And the third one is equals to 0, 0, 1. Clearly, you can see that this is a vector in 3 dimensions, 3 dimensions, 3 dimensions. So therefore, all of these belong to R3. Now, the question here is whether these 3 vectors span or generate B. In other words, are these 3 vectors enough to produce any vector in 3 dimensions, or to produce a vector like this in general? So therefore, let's say we have constants, C1, C2, and C3. So these are constants. So the question is this, is which these belong to R. So the question is C1 B1 plus C2 B2 plus C3 B3 enough to produce any vector in 3 dimensions? Remember, in general, a vector in 3 dimensions looks like this. And by the way, this is what we mean by a linear combination. Okay? So a linear combination of the vectors. So here K is equals to 3. All right, so what does this mean? Well, this is the same thing as C1 times 1, 0, 0 plus C2, 0, 1, 0 plus C3, 0, 0, 1. And this should be equals to ABC. Remember that here ABC is any vector. So you're trying to see if these 3 vectors, you combine these 3 vectors for given constants, you can produce any vector. Notice that this is equivalent to write it in matrix form like this. It will be 1, 0, 0, 0, 1, 0, 0, 0, 1. And then here you will have C1, C2, C3. And this one is equals to A, B, C. So this is very similar to the review what we did in linear algebra. This is technically A. You can call this X and this B. So notice that the determinant, so the determinant of A, and you should check this is equals to 1, which is not equals to 0, and remember the determinant is not equals to 0, that implies the system x equals to b has a unique solution for any vector ABC. So since this is true for any ABC or for any vector, this implies that the vectors b1, b2, and b3 span or generate R3 or any vector, so therefore they generate the whole vector space. Now there are multiple ways to show this part, that this can be solved, but the easiest way, or for the purpose of the class, the fastest and easiest way is probably to get the matrix A and check if the determinant is 0 or not. If the determinant is equals to 0, that means this doesn't have a unique solution, so therefore this will fail and this will not expand the system. But if the determinant is not 0, that means this has a unique solution, and therefore you can solve this system for any values of ABC, and that will imply that this generates or expands the whole vector space. Let's do a similar example, but in 2 dimensions, so you can see how this is not as bad as it looks. Now let's say that B is equals to R2, which are all the vectors in 2 dimensions. And let's say that we select the vector b1 to be 2, 5, and b2 to be 1, 3. And the question again is, do these two span R2? Okay. Remember that in general, you always need to look to this. In general, any vector that belongs to R2 looks like this: x, y, or AB, where x and y are any real number. So this is how it's supposed to look in general. So the question is, will these two vectors are enough if you do a linear combination to create any vector? Well, let's see. So again, if we use constants C1 times the vector, and then the second constant times the second vector, the question should be, can you solve this all the time? All right, so then this will be C1, this is 2, 5, this is C2, 1, 3. Okay. And then if we use the same trick, notice that here the matrix is going to be 2, 1, 5, 3. This is going to be C1, C2. This is exactly the same thing as the previous problem, actually even easier, because this is 2 by 2. So here, the matrix A is equals to 2, 1, 5, 3. The determinant of A is equals to 6 minus 5, which is 1. Again, this is not equal to 0. That's all that matters. So therefore, that implies that B1 and B2 span or generate R2. In other words, again, span just means that these two vectors, or these two, are enough to create any vector in 2 dimensions. Okay, now let's look to the concept of linearly independent. So a set of vectors, b1 to bn, again, remember by vectors, it means this could be vectors, this could be matrices, polynomials, and so forth, in a vector space, so you need to have a vector space now, are linearly independent if when you do a linear combination and you get 0, remember here 0 means the 0 vector. So this will be have a bunch of zeros, or it could be, if it is a matrix, it will look like this, or if it is a polynomial, it would look like this, and so forth. Okay. So implies that all the constants are equals to 0. So again, linearly independent means that if you do a linear combination and you get the 0 vector, that means that all the constants had to be 0. If that's not the case, then the system is called, or the set of vectors is linearly dependent. All right, let's look to R2 first. Let's say that B is the set of vectors in 2 dimensions. And let's say that we have the following vectors. B1 is 1, -1, and B2 is equals to 3, 2. The question is, are they linearly independent? Well, let's see. So you do a linear combination, which would be this, and you want to solve this equals to 0, 0. So the process is going to be very, very similar to what we just did with the spanning sets. So therefore from here we have C1 times 1, -1 plus C2 times 3, 2, and you want to solve this equals to 0. Now remember, when you solve something equals to 0 in a system of equations, this is technically the null space that we talked about before. So then if we write this in matrix form, we end up with the following. This is 1 - 1, 3, 2. And this is C1, C2. And again, if you find the determinant of A, you can check that the determinant of A, in this case, this will be 2 plus 3, which is fine. The point is that it's not equals to 0. So that implies that this system, in this case, the homogeneous system, has a unique solution. And since this is only one vector, and this has a unique solution, this implies that the only values for this system is C1, or the only values that solve the system is C1, C equals to 2, C equals to 0. So that implies that they are linearly independent. Or in this particular case, you can just solve this the old-fashioned way. Notice that from here you end up with the system C1 plus 3C2 equals to 0, minus C1 plus 2C2 equals to 0, and then if you do elimination, this will cancel. You end up with 5C2 is equals to 0. So that means C2 is 0. If you plug it into this equation, that means C1 plus 0 is 0. Therefore, C1 is equals to 0. Now, in this particular case, this actually makes more sense. It's more intuitive. But the reason why this is faster is because it's only 2 by 2. If the system was 3 by 3 or higher, then this will take longer to do, the Gaussian elimination. So therefore, it's better to find the determinant and check if it is 0 or not. All right, what about this one? So here are the two vectors, and again, as I say multiple times by now, the vectors don't have to be vectors in a vector space. It could be matrices or polynomials or any other object pretty much. So the question is, are they linearly independent? So again, we need constant C1 times B1. So you create a linear combination, and in this case, you want to check if this is true. You get a 0 matrix. So in this case, this is C1 is 1, 2, 3, 4, and then this is C2 times 3, 6, 9, 11, and you want to check if this is the case. Now remember, when you add matrices, this plus that should give you this, and so forth. So therefore from here we actually have C1, 2C1, 3C1, 4C1, and in this case you have 3C2, 6C2, 9C2, and 11C2, and this should equals to 0, 0, 0, 0. Again, this plus that has to equals to this, and so forth. So this implies that C1 plus 3C2 should be 0, 2C1 plus 6C2 should be 0, and so forth. 9C2, 4C1 plus 11C2 should be 0. Now this is not hard to check, and you should check this by yourself, that you can either use this system, you can just pick two of them, and you should check that C1 is in fact equals to 0 and C2 in fact is also equals to 0. So therefore that implies that B1 and B2 are linearly independent. Let's do another example. We have the same vector space, the set of 2 by 2 matrices, or the vector space of 2 by 2 matrices. So again, the question is whether these three vectors are linearly independent. So if we create a linear combination of these three vectors, and we end up with the zero matrix, or the zero vector, which in this case is a matrix with 4 zeros. And if it turns out that C1 is equals to C2 equals to C3 equals to 0, then these vectors are linearly independent. If not, they will be linearly dependent. Now, in this particular case, notice that we have a very extreme vector. We technically have a vector with 0, 0. So therefore, in this case, it is possible to get a zero vector with having, let's say, C1, 0, C2, 0, but even if, C3, 0, but the value for C2 could be anything. Could be 10, it could be minus 100, or technically any real number. It doesn't matter, it will give you 0. Why? Because anything times 0 is always going to give you 0. So this part is always 0, regardless of the value you pick for C2. So therefore, in this case, it is possible that C1 is equals to 0, C3 is equals to 0, but C2 doesn't have to be 0. So therefore, these three vectors are not linearly independent. They are actually linearly dependent. Right, let's do another example. Let's say that the vector space is the set of polynomials of degree 2 that have the following form. So again, if we want to check if they are linearly independent, we need constants C1, that when you multiply times P1, C2 when you multiply times P2, C3 multiply times T3, and P3, sorry, and you end up with a zero vector. Remember, in this case, this is the zero polynomial. Okay. In other words, this means this. You'd have C1 times T plus C2 times T squared, and then C3 times 4T plus 2T squared, and they should give you the zero polynomial, which in this case it will be 0t squared plus 0t plus 0. And then doing something very similar to partial fractions, you look to the coefficients. So for example, the coefficients of t are this. So that means that c1 plus 4c3 should equal to 0. If you look to the coefficients of t squared, it also has to give you 0. Then that means the c2 plus 2c3 should also give you 0. Okay, so now we have to solve this system of equations. So we can multiply the first equation by 1, the second one by -2. And from here it will give us c1 plus 4c3 is equals to 0. This one will give us minus 2c2 minus 4c3 is equals to 0. Clearly these two cancel. So this implies that c1 minus 2c2 should be equals to 0, or that c1 is equals to 2c2. So therefore, let's say that you pick c2 to be 1, so therefore that implies that c1 is equals to 2, which is clearly not equals to 0. So in this case, again, these are not linearly independent, they're actually linearly dependent. Since c1 is not equals to 0, c2 is not equals to 0, and you can check too that c3 is not going to be 0. So therefore, this particular set of three vectors are not linearly independent. Now, when it comes to check for independence, the next topic we're going to do right now, we technically have done this before. If instead of matrices or vectors or polynomials you have functions, you can in theory use the same definition to check for independence. Remember c1 b1 plus c2 b2 and so forth. But if you have functions that are more complicated than polynomials, this method may not be the best. So instead, we're going to use something that we used before. Remember, this is the Wronskian. We used this when we did the variation of parameters. And this is the determinant. So you have the function, then the derivatives, and so forth. So we have done this before. So therefore, this is a way more efficient way to check if two functions are linearly independent, or three functions, or four, and so forth. So for example, in this case, if we find the Wronskians of f1 and f2, first we have the functions here. So this is sine, cosine, then the derivative of sine is cosine, the derivative of cosine is minus sine. And then this is a minus sine square x. Remember, this is the determinant, minus cosine square x. So this is minus, you can factor the minus 1. So this is sine square plus cosine square x. Remember, this is equals to 1. So this is equals to minus 1, which is not equals to 0. So either Wronskian is not equals to 0. That implies sine x and cosine x are linearly independent. Okay, linearly independent. So therefore, every time you have functions, this is how you should check if functions are linearly independent or not. Otherwise, you will have to solve it this way. c1 sine x plus c2 cosine x equals to 0. And this is still possible, but it will be very, very, very messy. So this method is by far the easiest way to check if functions are linearly independent. All right, before we go to the next page, let's stop for 1 second and see what we've done so far. So far, we have covered two main concepts. The first one was spanning sets. Remember that a spanning set is a set that creates any vector on that vector space. And the second thing is linearly independence. So these are the two main concepts we have covered so far. So on the next page, we're going to put these two together to create something that is called a basis. All right, let's look to the following definition. A set of vectors v1 all the way to vn in any vector space V is called a basis for that vector space if these two conditions are satisfied. The vectors have to be linearly independent, which we know how to do that now. And also the vectors had to span V, which we also know how to check for that. It is very important that you check both conditions because it is possible for vectors to be linearly independent but not span the whole vector space. So therefore it will not be a basis. It is also possible for a set of vectors to span the vector space, but they may not necessarily be linearly independent, and therefore they are also not a basis. So you have to make sure you check both conditions. Okay, so let's do an example. Let's say that we have the following two vectors. v1 is the vector 1, 1, and v2 is the vector 1, negative 1. Let's check for linearly independent first. So let's check this first. So then if we have a linear combination of these two vectors, and remember you said this equals to the 0 vector, then c1 and c2 must be equals to 0 in order for this to be considered linearly independent. Now from here, this implies that c1 plus c2 should be 0. c1 minus c2 should be 0, so clearly here these two cancel. So you have to c1 is equals to 0, which implies c1 is 0. If you plug it back into this one, you can see again that c2 will be 0. So therefore, these two vectors are linearly independent. So this is okay. Remember, you can also use the matrix form to create a matrix. So this will be 1, 1, 1, negative 1. And it will be c1, c2. And technically you want to solve the homogeneous system, or in essence you want to find the null space. And from here the determinant of, let's say this is a, you can see is equals to minus 1, which is negative 2. This is not equals to 0, so that means that the system a capital C equals to the 0 vector has a unique solution. The only solution that this one will have, therefore, is that c1 is equals to c2 is equals to 0, and that will give you the exact same answer. All right, now let's look to see if these two vectors span the whole set. Okay. So remember that in general, any vector that belongs to R2 looks like this. So this is the general vector for R2, where x and y are any real numbers. So therefore, if these two vectors span the whole vector space, then c1 times 1, 1 plus c2 times 1, negative 1 should be able to create any x and any y. Here, we had to use the method I just described. So we have the matrix 1, 1, negative 1. This will be c1, c2. This is x, y. So we can say this is the system AC and I guess this we can call this B. So therefore, since A inverse exists, Y, because the determinant of A is not equals to 0. So that implies that C, which is equals to C1, C2, will have a unique solution all the time. And therefore this means that C1, that means that the two vectors, 1, 1 and 1, negative 1, span R2, because you can solve this system for any values of x and b. So remember, this one can be any x and y. Therefore, since these two vectors span R2 and they are linearly independent, then that means that these two vectors are considered bases for R2. Okay, now let's look to the following definition. The dimension of a vector space, which is denoted by dim B, is the number of vectors in any basis for V. Notice that it says any basis, which means that a vector space can have more than one basis. If V is the trivial vector space, which only has the zero vector inside, then we say that the dimension to that is equals to 0. Now, these are the most popular vector spaces that we looked so far. So this is a n-dimensional vector. This is a matrix that is n by n. These are square matrices. This is a set of polynomials, and so forth. Now, for the purpose of our class, since we're dealing also with differential equations, the dimension of differential equation that looks like this, or second order, is equals to 2, because it's second derivative. So if this was the n derivative, this will be n. The following definition is very important because it gives us another way to check if a set of vectors is a basis or not. So the definition says the following: if the dimension of the vector space is equals to n, and if you have a set of vectors that matches the dimension, if the number of vectors matches the dimension, then the following statements are equivalent. That means that S is a basis for the vector space, S is linearly independent, and S spans the vector space. In other words, if you have a set of linearly independent vectors that matches the dimension, then that set is automatically a basis. For example, consider, let's say that B is equals to RQ. The dimension of R3, because of this, is equals to 3. Okay, so that's the dimension. Now, remember that we have these vectors before, 1, 0, 0. B2 was 0, 1, 0. And B3 was 0, 0, 1. Now, since the dimension of this is 3, and the number of linearly independent vectors is also 3, that implies that B1, B2, and B3 is a basis. Now, for the purpose of the class, since we're also dealing with differential equations, okay, consider the following example. Let's say you have this differential equation, and everybody should know the answer is C1 sine x plus C2 cosine x. We already checked the sine x and cosine x in the previous page or the last two pages. These are linearly independent, and you have two of them. Now the dimension of y double prime plus y is equals to 2. Therefore, since the dimension matches the number of linearly independent vectors, that implies that sine x and cosine x is a basis for this differential equation for y double prime plus y equals to 0. Now, the last concept on this page is something called the rank nullity theorem. Remember that the rank is going to be the number of linearly independent vectors. So it's going to be the number of linearly independent vectors of the matrix A, of matrix A. And then nullity, this is going to be actually the dimension of the null space, and it has to equals to n. Now, the dimension of the null space is equals to 0 if the only solution is the vector 0, 0. So note the dimension of the null space is equals to 0 if or when x equals to 0, 0, 0 is the only solution to the homogeneous system. As I mentioned before, the bases are not unique. You can have more than one basis for any vector space. But every vector space also has something that's called a standard basis, and a standard basis is just the most simplistic way to, or the most simplistic basis for that vector space. For example, in R2, the standard basis is going to be 1, 0, and 0, 1. So this is the standard basis. But as you saw in the last examples we did, this 1, 1 and 1, negative 1 was also a basis. So you can have multiple bases, but this is the standard one. And the standard usually means the most simplistic one. For 3 dimensions, the standard basis is 1, 0, 0, 0, 1, 0, and 0, 0, 1, which is just an extension of this one. If you have a polynomials of degree n, remember that polynomial in this case looks like this. This will be a0 plus a1x, a2x squared, and so forth, all the way to anx to the n. Remember from the previous page, the dimension of this was equals to n plus 1, so it's important to remember that. And the standard basis here, which again is the most simplistic basis, is the following. It would be 1x, x squared, so pretty much just the powers of x to the n. Okay, finally, let's look to this example. The question is this a basis? And instead of checking the way we did before, we're going to use the dimension now. Remember that the dimension of R3 is equals to 3. So technically, all you have to do is check if these 3 vectors are linearly independent. If the vectors are linearly independent, then since the number of vectors is going to match the dimension, then this will be a basis. All right, so here, if you create the matrix A will be 1, 0, 1. This is 2, 1, 0, 0, 1, 3. And you should definitely check the following: that the determinant of A is actually equals to phi, which is not equals to 0. So that implies that the three vectors are linearly independent. Remember, this means linearly independent. So therefore, since the number of linearly independent vectors, which in this case is 3, matches the dimension, which is also 3, then that implies that the three vectors b1, b2, and b3 form a basis for R3. And that's it.